Hi, good morning, everybody. Thank you very much for attending Keio University Global Research Institute program, lecture series. This program is supported by Global Research Institute and the Super Global program and the Mirai Sendo Kikin. It's my great pleasure to introduce Professor Advincula to you. Professor Rigoberto Advincula is a professor of Case Western Reserve University in Cleveland, United States. He is a fellow of American Chemical Society, ACS, fellow of the Polymer Science and Engineering Division, and a fellow of the Polymer Chemistry Division. He is also a member of NACE, SPE, ERG, MRS, and AAS, and a frequently sold-out speaker, expert in polymer materials, coatings, and sensors. He recently has been appointed to the World Economic Forum Advanced Materials Council. He received the Herman Mark Scholar Award in 2013 from the ACS. He is the editor-in-chief of MRS Communications and also former editor of Reactive and Functional Polymers and Polymer Reviewers. His site and has previously served on the editorial board of a number of other major polymer journals. He has a total of 12,000 citations with a H index of 64. Amazing number. He was a chair of a polymer chemistry division, American Chemical Society in 2015, and is a committee chair with NACE. His group does research in polymer materials, nanocomposite, colloidal science, and hybrid materials, ultra-thin films, towards application from display coating to biomedical devices. He is also pioneering a number of 3D printing routes towards the new polymer and nanocomposite materials properties. He consults for a number of companies focusing on most challenging problems and the definition of a structural property relationships towards commercial applications. So, Professor Advincula, please.
Thank you very much, Professor Shiratori, for that kind and generous introduction, and also for hosting my stay here at Keio University. It is a pleasure to be here, and I would like to give this lecture on behalf of the class and for the students. Ohayo gozaimasu. Konnichiwa. Atsui tenki. I would like to give you an overview today of superhydrophobic coatings. And on the way, I will be introducing to you the type of research that we do in this area. But first, let me introduce to you Case Western Reserve University. So I am from Cleveland, Ohio. Case Western Reserve University is located in Cleveland, Ohio. And these days, the campus looks pretty much like this. Very green, not as hot. Maybe we have an average summer temperature about 72, 75 degrees Celsius, Fahrenheit. So that's about 20, 21 degrees Celsius. So I think you like that weather. But during winter, it's quite cold. Now, this is my area. We are located here in this building at the Macromolecular Science Engineering building. But we have a lot of interesting areas here that is very popular for Ohio people. One is the museum, Cleveland Museum of Art, and then the other, we have the Cleveland Orchestra, located right on campus. So we have a lot of art. We have the Lake Erie. We are very near the lake. This is one of the major lakes called Great Lakes area of the United States. And it is one of the largest freshwater body all over the world. And then, of course, we have orchestra. Now, there are several things you have to know about our campus. So some of the students have heard of this, so be quiet. But how many of you have seen the movie Air Force One? Okay. So if you have not, of course, you can Google it, but not right now. You have to listen to my lecture. Air Force One, the first part of that movie was actually taken at the rooftop of this building, Severance Hall. Okay. In fact, another movie, which is Captain America: Winter Soldier. How many of you have seen this movie? More. So the middle of this movie, the headquarters of SHIELD, they showed a very expansive building. That is Severance. That is inside the Cleveland Museum of Art. Okay. So if you watch Captain America movie again, you will see the inside of that building. And of course, this is our Hollywood version in Ohio. Okay. So it's a joke. Of course, Hollywood is in California. A long history. Case Western Reserve University started in 1826. We have a number of Nobel Prize winners through the years. In fact, the first American Nobel Prize winner, Professor Albertson, together Michelson with Morley, were professors at Case Western Reserve University. The founder of Dow Chemicals, Henry Dow, is a graduate of Case Western. Now, I will not have much time to talk about 3D printing today, but one of the pioneers in what we call makerspace, or making 3D printing available, not only as a rapid prototyping tool, but as a facility for students, we started this at ThinkBox. So at ThinkBox, we have a lot of major facilities, including 3D printing access, and much of my program these days relies on some of their equipment. I'm located in this building. This is Macromolecular Science Engineering building. My office is at the 5th floor, and I have 3 labs, and this is my current group composition. Now, as a professor, one of the things, of course, that I try to imbue the students is to publish papers, and why not? Every professor, like Professor Shiratori, of course, would like to see his students be successful. And so we have endeavored many types of fundamental research, not only applied research, but phenomena involving materials and interfacial chemistry. So a lot of things that we can do at the molecular to nanoscopic level can be done by utilizing dendrimers, polymer brushes, nanopatterning, the use of various photochemistry, and so on. On the other hand, my group is also involved with collaborating with industry. So a number of companies that we worked through the years are related to focusing on applied materials and interfaces, whether it be coatings, electromagnetic shielding, different types of sensors, and of course, superhydrophobicity. And some of these companies, of course, you will recognize as companies in Japan. And yes, I have worked with a number of companies in Japan through the years. After all, I have been visiting Japan for 20 years, almost every year. So what happens with a university is that we are able to take the best of the basic platform, not just research, but research platforms or methodologies and materials, then apply it to the market. And the way it is applied to the market is by bridging that gap through working with industry. And some professors have, of course, many patents, have started companies, and so on. And so in an engineering sense, this is an opportunity also for students to train on industry-related project. After all, we are looking for what we call cost-performance benefit ratio. So when you work in industry, you will find that the best value for your money or for your customer is to give them the best performance at the right price, meaning they will be able to pay for it because they want to. Okay. So in 2014, one of the things that I started at Case Western Reserve University is the institute called PetroCase. So this center or this consortium focuses on needs for the oil and gas industry. Oil and gas industry have many materials needs, not only to extract oil or to prevent corrosion or to convert oil to gasoline. Many things are needed in order to make efficient oil recovery, hydraulic fracturing, or the use of additives or fluids to make oil or gas flow efficiently. So it may not seem like good science, but believe me, there's a lot of science and engineering that is used for the oil and gas industry. After all, you cannot easily live without oil, and oil actually means plastics, okay? If you see plastics, you can say that it is related to the oil and gas industry. Okay, so let me start focusing now on coatings and surfaces. So why are coatings important? Well, obviously, this class is related to interfacial chemistry, and you are interested in the practical application of interfaces. Coatings is a word that can be tied to another term called packaging. What I mean by this is that on one side you have the bulk material, which could be water, milk, or it could be the food that you're trying to package. And then on the other side you have the environment, which is air, pollutant, liquid, and so on. So there's a barrier in between. On the other hand, when we say coatings, we can refer to a coated wall or a paint or a car, and they have a protective mechanism as well. That is, they protect the object from the effects of the environment. So on one hand, packaging means you protect the environment from the contents of the package, and then coating, you protect the contents of the bulk material from the environment. So there is a need to make this surface, interface, or coating, or polymer layer smart, or there is a need to make that effective. Maybe not so thin, but the thinner it is, and the higher the functionality, the more it can make an impact, maybe at the right cost, okay? So coatings, smart coatings, and the importance of engineering that layer, whether it's called packaging or coating, is important for both ways. So let me show you this collage which speaks about applications. So on one hand, in general, you want coatings to have a certain resistance to liquids or the environment. That is, you want to make them either self-cleaning or have the ability to prevent wetting. Packaging means that you need to make multi-layer barrier films, multi-layer plastic plus aluminum or metal foils to make the contents of the package last longer. Okay? You want them to have a higher commercial life. Automotive coating. So if you have a car, you don't want it to be easily scratched, or you want it to have a certain finish that gives you a style or gives you a color that you like. But more importantly, that coating is used to prevent rust and to prevent degradation, so your car will look shiny for many years to come. In the area of, let's say, skin, now skin is actually the biggest organ you have in your body. Okay? There's a big surface area in your skin. So for example, when it's hot, you sweat. It's because your skin is working. Okay? When it's cold, okay, you have the pores shut down, and also it has layers that provide insulation. So the skin is properly engineered as a coating, okay, for your body. And they are working properly, otherwise you will actually die if your skin is not working or it's prone to diseases such as infection, pathogens, or even allergy. And then lastly, this smartphone. Okay, how many of you have a smartphone? I think everybody. I have iPhone. Okay, and I'll tell you an interesting story. Okay, I'm not even sure if this was a Samsung phone, but when I was first a professor, I had one of my first students who did a lot of work on LED. LED stands for light emitting diode materials or polymers. And one of the things that he pioneered was a lot of polymers that are blue emitting or very efficient blue emitting. So the LED, let's say in Samsung, owes itself to one company. Samsung and LG basically uses organic materials from a company called Universal Display Corporation. Universal Display Corporation is based in New Jersey, USA. So the head of the R&D for Universal Display Corporation in the area of smart LED materials was my former student, was my first student, okay? So that means a device like LG or Samsung makes use of that OLED material. Well, you should ask me, I should be using Samsung, right? Because my first student was involved in the development of Samsung. But I'm using iPhone from Apple. The reason is because my wife said I should use Apple, okay? So that's the only reason. All right, so there's a lot of coatings that can be found in your smartphone. So for one thing, when you call, okay, when you try to type, it becomes dirty, okay? It smudges, a lot of oil, a lot of fingerprint. So your smartphone actually has a very thin coating. Even though it's glass, it has a very thin coating of silicone. Or sometimes a perfluorinated coating to prevent, to make it more smudge-free. Okay, so other than that, let's go molecular. So nanostructuring polymer ultra-thin films means that you are able to order up to the nanostructure level or the nanometer level. Okay? Actually, Professor Shiratori and I share many things, not only with the interest on superhydrophobic coatings, but we both work in the area of layer-by-layer films. And even many years ago, probably he did some work on Langmuir-Blodgett films. But here you can see that one of the ways you can modify a surface is through chemistry or chemical adsorption or chemical reaction. So this can be in the form of silane coupling or self-assembled monolayers or the use of epoxy or other reactive groups to build layers. Another way to modify a surface at the nanostructure level is to deposit a very thin monolayer of surfactant or polymer or what we call Langmuir-Blodgett film. This means that the material has to be equilibrated at the air-water interface, and then it can be picked up by vertical or horizontal drawing, which we call Langmuir-Blodgett or Langmuir-Schaefer. And then another method is by the use of polyelectrolytes. Now, polyelectrolytes can adsorb on surfaces where you have opposite charges. if you have the same charges, it will repel, or electrostatic repulsion. So because of ion exchange, you build up layers pretty quickly simply by alternating negative and positively charged polyelectrolytes, nanomaterials, or even amphiphiles. Another way to build up thin films is by vapor deposition. It can be chemical or physical vapor deposition. That means you evaporate the reactant and the reaction occurs such that during the polymerization, condensation, crystallization, or sometimes we call it sublimation, if it's a physical property, you deposit a thin film. Another way, of course, is physical vapor deposition. So you can evaporate a polymer based on control of the vacuum or vapor pressure. Now, there are two methods here that we have done a lot through the years that I would say is a big contribution of my research group. That is in the area of electron nanopatterning. So we have developed many methods for electrodepositing polymers precisely, site selectively, and also time dependent. We can make different types of precursor polymers that prepares thermoset conjugated polymers even on patterned surfaces. The other technique that we did a lot and many other groups is in the area of polymer brushes or polymer grafting. Polymer brushes means that we can prepare initiators on surfaces and then cause the polymer to grow from the surface, just like hair, you know. Hair comes from your head, so you can make polymer grow from the surface. That's called grafting from approach in polymer brushes. So you can see here that polymers play a very important role in nanomaterials and interfaces. So when we talk about interfaces, interfacial phenomena, or even colloidal phenomena, we should not forget the role of polymers. Polymers are essentially large molecules. Large molecules means they like to stretch, okay, or they like to fold or become contracted or compacted. This is because polymers exhibit a hydrodynamic volume. That is, they interact with the solvent, whether it's a theta or a non-theta solvent. In one occasion, you can have a polymer forming films or forming polymer brushes, a thicker film involving layering or structuring to form blends or polymer brushes with different grafting densities. And then this can result into membranes or thicker films. In other words, from the nanometer level and up, you can make polymers stand up or lie flat or produce different types of collapse regimes. Now that's the film side. The other side is you can see polymers playing an important role in colloids or particles. So polymers can swell or contract based on its interaction with the solvent. It can complex with other polymers or other nanomaterials to form complex gels or hydrogels, or you can cross-link this gel to form a nanogel. In other words, polymers play an important role in the balance between the hydrophilic, lipophilic interaction on the interfacial phenomena. So you can have polymers that can be miscible or immiscible with various solvents, or you can have very stable Pickering emulsions that can stabilize emulsions in oil and water. So truly, we can say that a polymer is a nanomaterial. It is capable of interaction and manipulation at the nano level, much like we can use carbon nanotubes, nanocrystals, gold nanoparticles, graphene, etc. I can see, or you should see polymers in the light of this type of nanomaterials. Okay, so with that in mind, let's start moving into superhydrophobic materials. So let's first talk about superhydrophobic coatings and applications. Okay, superhydrophobic effect. Some of you would have encountered this or have taken this in your class. Has many various applications and potential for improving many products. Super hydrophobic, meaning it hates water with a passion. It hates water where the definition is such that it is non-wetting and there's a particular contact angle that they reference for the super hydrophobic effect. They say, or an arbitrary number that has been agreed, a number that has been agreed by many researchers is that a contact angle of 150 degrees is enough to label a material super hydrophobic. Now, super hydrophobic can also mean self-cleaning, or you have a tilt angle or a dynamic value that changes, and especially with the incline of the plane of wetting, result in roll-on, roll-off angle that constitutes self-cleaning systems. So as you can see in this collage, we can think of many ways that super hydrophobic effect can be harnessed. From paint to marine environments to carpeting cover to fabric maintenance or different types of icing, de-icing application, anti-corrosion application, fibers that are efficient in heat transport or insulation, and so on. So you can see here that the super hydrophobic coating has many potential applications. And the real question is, can you keep it? Can you maintain it? Can you have long-lasting super hydrophobic effect in a material? Now, in many ways, of course, this means that we have to mimic nature. And we have to look at what has been observed, let's say, with a lotus leaf, and then convert that into a surface that is durable. Durable means that you are able to maintain this contact angle greater than 150 to classify it as a super hydrophobic material. And essentially, if you have a roll-off angle of less than 10 degrees, then it can also have a self-cleaning property. Now, I'm going to talk to you later more about the Casey-Baxter, Wenzel, and Young's equation modification, which some of you should be familiar. It has to do with the ability of wetting that is dependent on the surface hierarchy of nanostructuring and roughness. Essentially, an ideal Young's equation, as you'll see later, where you have an essentially flat film, the work of adhesion is aided by a strong interaction on a surface. On the other hand, the failure of adhesion can be related to the failure to form line tension, a continuous line tension or surface tension, and in the presence of trapped air results in this super hydrophobic effect. So actually not only lotus leaf, but you find this reference in many types of natural surfaces or phenomena. Take the case of butterfly wings, birds, different types of insects, like the insect strider, different morphologies that result in this hierarchy of roughness, and essentially looking at the Casey-Baxter approach means that we can make a surface super hydrophobic even without invoking surface energy. That is, surface energy or surface chemistry is just one attribute that can be brought into the equation. So let's start with looking at an ideal Young's equation. So an ideal Young's equation shows that you have the basic relationship between the surface tension or interfacial tension, where you have the surface tension related to the solid and air, balanced by the solid and liquid and air surface tension. That is given by the cosine theta of this direction versus this direction, resulting in this Young's equation. So the Young's equation has many assumptions. One assumption, of course, is that you have a solid plane, independent or in the absence of roughness, giving you pure surface energy calculation without the correction for the effect of roughness or trapped air. Now, what happens when you have roughness on a surface? So, by the way, so this is how we call something as hydrophobic or hydrophilic. Hydrophilic will have a wetting value which is less than 90. Hydrophobic is greater than 90, or you say towards that direction. A zero wetting, a zero contact angle means it's a totally complete wetting or sometimes super hydrophilic property. When we say hydrophilic, we're referring only to water, okay? There's another term that I will introduce later. It's called oleophilic and oleophobic, meaning oil. So one extreme you have wetting by water, and the other extreme is you have wetting with oil. And of course, in between the two, you have many other solvents based on polarity, okay? Non-polar or polar. So hydrophilic, again, is a term. Hydrophilic and hydrophobic is a term associated with water wetting or non-wetting. Now, the second type of interaction is basically accommodating the effect of roughness. So if you have a surface that is not homogeneous in surface energy or not flat, when you introduce this roughness factor, let's say when you do this correction can appear on this side of the equation, or R times cosine theta, giving you what we call the Wenzel model. Now, this correction is important because you have to accommodate for the change in the surface area. The roughness is defined by the actual surface area and the projected surface area. So if you have a value of R equal to 1, then there's no correction. But if you have an R value greater than 1, then definitely there is a surface effect based on the Wenzel correction. The third approach for accommodating wetting behavior is taking that roughness factor and then adding a correction based on trapped air or volume of air that prevents, again, wetting or the formation of a continuous line tension between the liquid and the surface. That correction can appear here, which essentially is a fraction of the solid-liquid contact lost or accommodated by the volume of air that is trapped in that rough or hierarchical roughness found on a surface. So we call this a Casey model or Casey-Baxter model, where you have not only the roughness but also the volume of trapped air as part of your correction factor. So not looking at the correction factor, basically the Casey-Baxter model is the basis for a lot of superhydrophobic properties where you have non-fluorinated surfaces or the absence of a low surface energy such as fluorine or silicone, okay? So we will give many examples, or you will look at many examples today to see how superhydrophobic surfaces are created using or basically taking advantage of what we know with the Casey-Baxter approach. But first, let's summarize all of this in this one page. So here, you can, in one view graph, you can see the Young's equation in its basic form. the correction with roughness based on the Wenzel model, and then the correction together with the roughness as well as the area accommodating the volume of air or interspatial volume called the Cassie-Baxter model. Okay, so this basically summarizes the past 3 slides. Again, we are talking here only of super hydrophobic or water phenomena. What about oil? What about nonpolar solvents? Well, the opposite can be held true, okay? But in this case, we are talking about non-oil wetting or super oleophobic coating. So the technology you have in your smartphone in many ways was developed to have or to prevent oil wetting, because most of what you get from your hands or from your face is basically oil. Okay? A lot of oil is generated by your skin. Okay? Or lotion, or when you eat food after or while eating your ramen, you put your hands here, you have a lot of oil. So super oleophobic actually is very important in many solid state display or other applications where you have contact with glass. So for example, you can see here that in many ways, super oleophobic coatings are equally important. Okay? But today, of course, we will not talk about super oleophobic coatings, and there are ways to do that. And you can basically try to reverse the effect by playing on the surface energy again, and the roughness and the surface energy, but this time against oil and other non-polar organic liquids. Okay, so let me focus now on looking at the different fabrication methods for making super hydrophobic films or coatings or surfaces. And then after this, we're going to look at some applications where it is applied in industrial settings. And then finally, I will close with some of our work on super hydrophobic coatings and oil and water separation. So how do you fabricate super hydrophobic coatings? There are several routes. This includes electrochemical deposition, electro spinning, wet chemical reaction, hydrothermal synthesis, phase separation methods, layer by layer assembly, colloidal templation, sol-gel methods, casting, solution immersion methods, to name several. And obviously there are many other methods here that I'm not including in this list. The bottom line is that there are many routes towards super hydrophobic coatings. And usually, to look at them in a practical sense, the biggest question really is how long do they last? Do they last forever? Or do they maintain their super hydrophobic effect for hours, days, or weeks? Or are they easily destroyed? Or are they easily fouled? Okay? So that is really something for you to judge, or something for you to take as a challenge. How can I make a super hydrophobic coating that will last for a long, long time? Okay? Even I, or even Professor Shiratori, that is a big question we're trying to target, or we're trying to find solutions. And many people in industry would like to see it. In fact, I will introduce a term here. It's called omniphobic. Omniphobic meaning it's super hydrophobic and it's also super oleophobic. It hates water and it also hates oil. If you have such a surface, you will become rich, because that can be applied to many types of situations, including your smartphone, okay? So if you can develop what we call omniphobic, okay, or ultraphobic, okay, it just hates water, hates oil, hates everything, okay? It's a loner. It doesn't like other surfaces or other media to touch it. That means you can use that in many, many applications. Okay, so let's take the first example. How do you use electrochemical deposition? So one of the ways, as demonstrated in this paper, is that you can develop zinc oxide nanostructures in an area that has been etched and includes electrolytes that results in this type of nanostructuring. From dots to nanowires to nanoflowers, you will end up basically with a hierarchy of structure. Now, electrochemical deposition is not only for metals. Electrochemical deposition can be used with polymers. And actually, the type of superhydrophobic effect that we have made is based on electropolymerization on surfaces or electrodeposition of polymers on surfaces. So here is the principle. If you are able then to create this hierarchy of roughness with electrochemical deposition, then you are able to create non-wetting environments. Another is based on electro spinning. So electro spinning makes use of a high voltage between the target and the solution source, let's say 20 kilovolts, 10 kilovolts, 20 kilovolts, such that during the injection or exit of the solubilized, let's say, polymer, you form very, very thin fibers or ultra thin, if not nano fibers. These nanofibers provide different types of volumes and roughness that allow one to have also a high contact angle. The high contact angle can be achieved essentially by using, in this case, a fluorinated silane together with a electrospun fiber. So you can combine different types of fiber material, nanofiber material by electrospinning or other methods, and then you can further modify the surface energy by using silane agents. Okay? So all of these surfaces, except for the two above, which is below 150, clearly exhibited a superhydrophobic effect. Another method is based on wet chemical reactions. So in this case, a superhydrophobic rough structure was prepared from a copper wafer via etching with nitric acid and a surfactant. The surfactant essentially has the role of forming different types of emulsions, or surface structure rather, and the use of perfluorododecyl triethoxysilane produces a low surface energy. So in this case, the combination of a surfactant and an etching agent such as nitric acid, and lastly with the modification of a fluorinated silane agent makes it superhydrophobic. Okay, another example. This one is based on hydrothermal synthesis. Hydrothermal synthesis, in this case, tungsten oxide nanostructure films were prepared on alumina plates and tungsten foils using a hydrothermal approach. What happens is that you control the adsorption and deposition as well of dodecaine thiol associated with silver that's deposited on the tungsten oxide surface. So of course here we don't have the SEM structure or optical microscopy, but you can guess that underneath the surface here you have a roughness factor that has also been modified with the presence of the dodecaine thiol. Another method is based on phase separation. So phase separation can be done with essentially liquids or polymers and liquids that have an immiscible property. In this case, styrene and a copolymer was prepared in bulk, and because of their phase separation, when you dry them as film, they form these types of morphologies. These morphologies or microstructures is based on the inability of the copolymer to separate itself between water and THF. So after drying, you end up with a surface like this, and the microstructure of the polymer film results in, again, super hydrophobic qualities as shown in these systems. Okay. Self-assembly and Lbm methods. This has been demonstrated easily by alternating layers of polyelectrolytes and silicon nanoparticles. So you can take a cotton fiber or even paper, and then after depositing the polyelectrolyte, this was modified with a fluoroalkyl silane treatment. The morphology together with the silicon nanoparticle results in multi-layers of particles and polyelectrolytes, enabling it to have a super hydrophobic effect and a hysteresis lower than 10 degrees. So you can clearly see here the droplet being unable to form a wetting on the fabric, but more importantly, when you take that fabric and you dip it in water, the unmodified fabric has the water contact line going up, whereas the super hydrophobic fabric, you see a silver colored texture here, indicating a lot of air bubbles or trapped air during the dipping. And that again is a consequence of the super hydrophobic effect. So in these past examples, at least you can see several things. One is by employing methods that results in a hierarchy of roughness, you can take advantage of the Cassie-Baxter approach. And then usually the last treatment, which they do, and in many cases is actually not needed, is they employ a low surface energy surfactant or amphipal or modifier to further increase the non-wetting behavior. That is a Young's equation approach. Okay? So the combination of the Cassie-Baxter and the surface energy approach allows you to make these surfaces pretty much from all these methods that we've covered so far. Okay, solution immersion method. Now this time, the procedure is inexpensive in that the surface of a substrate can be modified by different solutions, usually with the aqueous dipping in sodium hydroxide and copper nitrate. What happens is as you alternate the copper foil between these two solutions, you end up etching and providing this rough structure. Again, this was modified with the use of a perfluorododecyl trioxysilane to produce this super hydrophobic effect. In this case, a contact angle of about 160 to 63 rather is even observed. Now, I don't have the values on the tilt angle by which you demonstrated self-cleaning, but of course we can go back to each of these publications and see how they measure the roll-on, roll-off angle for each of these super hydrophobic films. Okay, sol gel. What is sol gel? Sol gel uses, again, silane precursors like TIOS or EOS or any alkoxysilane agent. Sol gel is a combination of two words, solution and gelation. It is actually the way you can make a aerogel and a serogel depending on the formation of a film before or the formation of a foam or gel with a lot of air volume resulting in an aerogel. In this case, the sol gel was prepared using colloidal particles and aggregates with aminopropyl trioxysilane. The aggregates were formed and then finally heated and cured such that you have a thermoset or a cross-linking between the sol gel material and the particle. The result is you get, again, a structure, a hierarchy of structure that gives you this super hydrophobic effect. Now, what is interesting with this method is it's transparent. Okay? So the sol gel method is one of the best ways to modify glass or to make super hydrophobic coatings on glass because of the high transmission. Okay. And yet another method is based on spray casting. So spray casting can be done using carbon nanotubes solution together with polystyrene, and you simply spray the material. The result again is you get a hierarchy of roughness, and here you have the demonstrated super hydrophobic effect, but they also highlighted the sliding angle less than 3 degrees, meaning this is also a self-cleaning surface. Now, the use of the carbon nanotube and polystyrene provides a high transmission surface because a very, very thin layer of this carbon nanotube and polymer film allows it to maintain its transmission properties. A carbon nanotube is essentially black or greenish in color. But with very, very thin carbon nanotube coating, you can still have a high transmission behavior. Okay, so I have shown you at least 8 methods of making super hydrophobic films. What is your favorite? Or what is the method you use for your research? Okay, or what is the easiest you have seen so far? Okay, maybe I will ask that question later. Or you have a question? Okay. So start thinking, okay? Among the methods, what can you identify with as a research method or research topic? Or what among the methods here impressed you as something that you can do in a practical sense, okay? So you might ask, is there something I can buy from the store to make a super hydrophobic coating? Can I go to Don Quixote? Okay, where else we go? Family Mart or 7-Eleven? Let's say if you go to Donkey and ask them, do you have a super hydrophobic spray coating? I think they actually do. You go to the shoe section, okay, shoes, okay, and look for a product that you spray to prevent oil or wetting or ketchup or whatever from staining your shoes. I think you can, okay? Try to go to Donkey. But in the US, we can go to Home Depot and we can order this product. It's called Never Wet. So you can Google it in YouTube. Not now, later, okay? Never Wet. If you look in YouTube, Never Wet is a product from a company called Rust-Oleum. Rust-Oleum has many products for anti-corrosion, paints, and home or do-it-yourself kit. This is a 2-step spray. The first spray prepares the base coat or the material for the actual super hydrophobic effect, because this type of treatment can be used on many surfaces, from rubber shoes to clothes to your face. No, you don't want that. To any material. So you need to prepare a base coat, which is basically the primer. And then after you prepare the primer, you then spray the second part, which we have tried to deformulate. It actually contains silica nanoparticles. We've known that. But you can deformulate this. This essentially will create a rough surface, a hierarchy of roughness. And perhaps they included some silane agents that are of low surface energy. The cost of this in the United States, probably about $20. Okay, so this Never Wet, I don't know if it's available in Japan, but you can try and see it from maybe Amazon. Maybe you can buy it from Amazon. There are many companies out there. And I'm not familiar with the companies in Japan, but I'm very sure there are many companies in Japan who also have commercial coatings. So this one is called Hydrobead. Okay? Hydrobead is a paint product or a coating product that again can be applied on a surface, and they claim to have longer lasting super hydrophobic properties as well. It's used to prevent ice, prevent rusting, antimicrobial, self-cleaning, water repellency. So by the way, of course, we don't have much time to look at some of the applications in detail, but one of the things that we know works very well for super hydrophobic surfaces is antimicrobial. And sometimes, well, not antimicrobial in the sense that it kills bacteria, but it prevents biofilm formation. Okay? The super hydrophobic effect is good in preventing infection or preventing degradation from pathogens forming biofilm. It's also good for preventing rust. That is, you can stop corrosion when you apply it on a steel surface or a metal product. So the anti-corrosion property simply stems from the fact that you prevent the corrodant from water from diffusing to the coating surface or metallic surface. And then ice prevention. And we will have many examples of that, I'm very sure, and we'll look at some very soon. Now, another company is called Hydrophone. Again, this is a commercial available coating. One of the ways that this coating has been used is because of its high transparency and optical clarity. Okay? So this is a company, again, that shows a aerospray or a dipping coating product, or it can even be used as a low viscosity ink in certain applications. So you can see here the many potential applications of super hydrophobic coatings. Okay? Super hydrophobic coatings in marine environment, in transmission lines, in heat exchangers, different types of anti-corrosion, anti-graffiti application, different types of de-icing, protection of solar cells, etc. Let's focus a little on anti-icing applications. Okay? So why do we want to prevent ice? Why do we want to prevent condensation? So actually, not only for oil and gas, especially LNG. LNG stands for liquefied natural gas. So here in Japan, you actually take shipments of natural gas from the United States. But for the gas to come here to Japan, they have to compress it. They have to bring it to a supercritical temperature so that it's liquid. Otherwise, they cannot transport here a gas with a big volume. So they compress it, they put it in an LNG storage unit, and then they transport it by ship. That means during the expansion of the gas, there's a lot of ice that's developed. So there's a lot of ice in the gas industry, believe it or not. But where else do you find ice? Ice is found in a lot of superstructures. It's found in airplanes, it's found in ships. So anti-icing, de-icing applications are important. So you can see here different surfaces, a hydrophobic surface, a super hydrophobic surface, flexible, and a rigid super hydrophobic surface. This means that if you prevent liquid from nucleating the surface to form ice crystals, one of the ways to prevent ice formation is to basically repel them in the first place, or to prevent condensation. Now, a rigid versus a flexible super hydrophobic surface actually has some merit. The reason is that the thermomechanical properties of expansion and contraction of a surface can play a role in the size of that nucleated droplet or nucleated ice. So the substrate effect cannot be underestimated for anti-icing application. Now, this can be tested, of course, in several ways. One is, of course, by direct exposure to the iced environment. Put it in a refrigerator or put it in a snowstorm. Or you can use supercooled water, for example. Simply pour that on a surface, and then you can observe whether the ice forms upon exposure to the atmosphere and resulting in ice crystals, or adhesion rather of ice crystals on the surface. Here you can see two aluminum plates. One was coated and the other one was not coated. And here you can see one supercooled water is poured. As soon as the supercooled water contacts the aluminum plate, you form ice formation when the supercooled water impacts the plate itself. However, if you have a coated or superhydrophobic surface, you don't see the formation of the ice which only occurs near the edge. In other words, when you first pour the supercooled water, you don't form an ice. And this is just one of the ways that has been used to demonstrate anti-icing application in such surfaces. Again, if you examine the coated surface, you'll find this hierarchy of roughness that was coated on the aluminum plate. Now, here you can see some practical applications. So outside, maybe if you go to Hokkaido in winter, certainly in Cleveland, we have a lot of ice. You want to protect the transmission lines. You want to protect the antenna. You want to protect the roof. You want to protect the window, okay? So many of the treatments that beyond aluminum can take advantage of the superhydrophobic effect. And many surfaces, essentially, if you have a superhydrophobic coating, results in the availability of air or trapped air in between the solid rough surface, or let's say employing the Cassie-Baxter approach, preventing the ice crystals from forming in the first place. Okay. So here are static tests. There are other tests based on wind tunnel, based on shear forces. There are other applications that merits tests based on ASTM standards or FAA. FAA is the aviation body in the United States that approves a lot of coatings and a lot of paint used for aircraft. Or the military, actually the US military has one of the biggest uses for the superhydrophobic effect. Not only for anti-icing, but different types of mitigation for corrosion and destruction in many environments. Okay, can you use superhydrophobic effect for reducing friction? Okay. Yes, friction based on shear flow, and I'm not going to show you the data here, but suffice it to say, laminar flow is an ideal flow for liquid that is passing through a pipe. Turbulent flow actually is not good because it can cause cavitation and corrosion. But just some examples in that the use of superhydrophobic surfaces can reduce friction to as much as 75%. Now you may say, is that important? Is friction really important? It is. Friction is important because a large amount of friction in pipes means high energy pumping. Means you have to spend powerful pumps to pass the liquid from one end to the other. But by reducing friction in pipes or during transport of liquid, you are saving energy. Okay? You want to save energy? Just don't recycle plastic. Well, you can also save energy by using superhydrophobic or developing superhydrophobic surfaces in pipes, whether it's oil, emulsion, okay, or even water. Water has many issues when you are transmitting it from the water treatment to your home. It encounters a lot of scaling. a lot of corrosion. Okay? So imagine if you have a pipe for water which does not have any scaling or any corrosion. That means water will flow without impediment from the sewage treatment, from the water treatment plant to your home. Okay? So oil, water, emulsion, any form of liquid, as long as you can reduce the friction between turbulent and laminar flow, you actually save a lot of energy. Now let's look at another example, heat transfer. So many types of heat exchangers are necessary to exchange heat, okay, for cooling or for different types of process industries. The high surface area of heat exchangers are sometimes forgotten or taken for granted. For one thing, a lot of heat exchangers are prone to corrosion and scaling, meaning if you have a heat transfer eventually in a supersaturated water environment, inside these holes here are many pipes going that direction. And one of the easiest things that get damaged in these pipes is that there's a lot of scale. So you have to clean them again and again, or you have to replace them, or you have to retube them. So one of the interesting uses of superhydrophobic surfaces is actually for heat exchanger or making efficient heat transfer. It can be seen from this figure where you have a superhydrophilic, a hydrophilic, a hydrophobic, and a superhydrophobic film. What are the differences? A superhydrophilic or hydrophilic film, you don't see bubbles. Why? Because water is in direct contact on the surface. And that means that you have very high contact, and therefore a lot of the heat, for example, is lost in water. Now, that's good if you are using water for cooling. Okay? But what if your motivation is to get as much heat transferred from one point to the other? In a superhydrophobic film and a hydrophobic film, you see a lot of bubbles. But here, you don't see a lot of bubbles, but you see a silver film. That silver film simply means it's all coated by air. Okay? There's a lot of air and then water. Here, there's a lot of water in contact with the surface. The difference is that this, essentially air being the #1 insulator, means that you have efficient heat transfer. Or heat transfer. Heat transfer not between water, but between whatever liquid or media that is passing through the pipe because of that insulation. Okay, here's another manifestation of that, except that it shows the region by which you have the amount of heat and the number of active nucleation sites being very low for a superhydrophobic surface versus a hydrophilic and superhydrophilic surface. Now let me take this last example. So what if you have a pipe and your goal is to condense water, okay? You want as much water collected from that pipe. Now, I'll give you a good example. Right now, you're in this room. It's cool, okay, because of the air conditioner. But when you go outside, if you look at that air conditioner, there's a lot of water. Where is that water coming from? Well, that water is condensing water from the high humidity, okay? There are many areas in the world, for example, that do not have water, desert. Okay? And they have developed technologies to collect water from the atmosphere. Basically, they want to collect as much water from the humid environment in the night, and then that water condenses, and they collect it with a bucket of water, and they can drink it. Okay? So that means we want a lot of water. So take this example here. If I have bare copper, you see the liquid just coating the copper. Okay? And what's happening to the liquid? Well, the liquid is not dropping. The liquid basically forms a film which prevents the bare copper from collecting a lot of water. Now, if we make this bare copper hydrophobic, you start seeing droplets. Okay? You start seeing droplets. And then eventually those droplets collect to form bigger droplets, and you get water. Now, what about a superhydrophobic film? Well, in a superhydrophobic coating on copper, we don't see anything. Why? Why is it that we don't see anything? We don't see anything because the water already dropped. Okay? It is so efficient in condensing water that as soon as the water touches it, the water drops. That means I will collect more water here than here, and certainly not here. Okay? So you can see the super hydrophobic effect is very useful for collecting water. And you can use it in the desert, or you can use it in the night to collect a lot of water in a humid environment. Okay, so with the remaining time, I still have about 10 minutes. I can briefly show you what we have done to make a super hydrophobic film. So thankfully, I'll skip past this introduction. So take the case of lotus leaf, okay? And the surface of the lotus leaf looks like this. Can we template? Can we copy? Can we make fake leaf, okay? So this relies on the Cassie-Baxter phenomenon. And here is the steps that we've taken. Actually, some of the students will be on the next lecture. I'll explain more of this. But for now, if we take a PDMS mold, we replicate the lotus leaf. We can take that PDMS mold and then stamp it on a cellulose acetate film. That cellulose acetate will be a replica of the lotus leaf, okay? That replica is actually artificial. It's already a polymer. And then we coat it with polyelectrolytes that are also initiators for ATRP. ATRP, I'll explain later, is a way of making polymer brushes. So we grafted a polymer brush of polynipam. And the polynipam essentially coats the artificial lotus leaf that was made from cellulose acetate. So how does it look like? It looks like this. So original lotus leaf and then fake lotus leaf. Okay, you can see the polymer brush here. And then we use a technique called IR imaging to verify the material. So this is our way of making a fake lotus leaf. Okay. Now, what's interesting about this fake lotus leaf? Well, what's interesting is based on the temperature, we can make it wetting or non-wetting. Okay. Polynipam is a polymer that has what we call a lower critical solution temperature. So here is a surface that was not modified, and you can see that it actually shows a good change in wetting behavior from 60 to 90 simply based on the polynipam action alone. However, by using a lotus leaf-like surface, you get a very high wetting change from 0 superhydrophilic to 153 superhydrophobic based on a 15 degrees Celsius change. Okay? So just simply by changing it to 15 degrees Celsius, we can make it super wetting to super hydrophobic. And we can do this back and forth. Okay? So you can see here that this cyclical behavior was afforded by that very, very thin film of the polymer brush of polynipam with a lotus leaf-like structure. And we can do this in other types of mimics, for example, insects and bird and feathers and so on. Okay? So these are fake but smart, go to sleep. Okay. So quickly, this one, we made these colloidal templates based on particles that are made by emulsion polymerization. So these surfaces look like this upon electropolymerization of a conducting polymer. So polypyrrole is a conducting polymer. It's not fluorinated, it's a conducting polymer. And we can make this on a surface. Now, one of the polymers we deposited is polythiophene. Polythiophene, again, is a non-fluorinated polymer. This is an example of an electropolymerization. And what we got is we got surfaces that are super hydrophobic. Okay? And I'll explain to you some of the experiments we did. But more importantly, it's super hydrophobic, but it loves oil. It's super oleophilic. Okay? Super hydrophobic, but super oleophilic. Now, those of you who will stay or who will attend the lecture after, I don't know if it's in the same room, maybe you can hear more about this. So I'm going to skip some of these slides in order to save time. Okay? Another material that is non-fluorinated is polybenzoxazine. So this polymer is a thermoset. It's not fluorinated. It's a thermoset based on a benzoxazine chemistry that we developed together with silica nanoparticles and graphene. So it has a very high adhesion, very good ASTM DT359 values, but more importantly, it's a super hydrophobic thermoset. And again, I'm going to skip some of these slides, and I'm just going to close by this. So we used that slide, and then we sprayed a wire mesh, 150 micron wire mesh. We sprayed the coating on this wire mesh, and we can make gasoline, kerosene, oil, nonpolar solvent pass through, okay, just by gravity. So if we color oil with orange, it passes through. But when we added water, which was colored blue, it did not pass through, okay? And then we mixed the two, oil and water. Only the oil went through, okay? So these are very good oil and water separators. And we actually repeated this on another formulation, which again, I'm going to discuss on my next lecture. So we've run out of time, and I apologize if I had to skip some slides. But basically, what I have described is super hydrophobic phenomena, its applications, principles, and hopefully it inspires you to use them. So with that, I'd like to thank you. Arigatou gozaimashita.
Thank you very much, Professor Advincula. So now, ask him any questions. Are there questions from students?
Hi. Thank you for the very informative lecture. So I have a few questions, but I'll just ask two in case someone else wants to ask questions. So I thought it was really interesting to see a lot of fabrication methods. Like, I didn't know there were so many. But so I think most of the people here don't have a chemistry background. And I noticed that a lot of the methods involve some kind of chemical solvent or method with revolving around chemistry knowledge. And I was wondering how much do you think is possible to achieve in the thin film industry without this kind of knowledge and just experience in like physics or mechanics?
Okay, a good question, good point. The methods I've shown you were optimized methods that, for example, uses as the last step some type of silicization or self-assembly. On the other hand, the last step that I showed you here are the example in our group does not require much chemistry. It really involves as simple as mixing two ingredients, making a flat film, and then you get a coating. I would say it's possible to observe the superhydrophobic coating in lithographic methods, in different types of vapor deposited films, or the use of mechanical rubbing, okay, in some occasions. But in order to optimize, you have to do some chemistry. That chemistry can involve the step towards cleaning asperites or removing things that can actually foul the surface, or in the case of many examples, as a last step in order to optimize the superhydrophobic effect.
Okay, can I have another question? So this isn't a really nice question, but I feel like it would be, this is just my opinion, but I always feel like it's more profitable if like the superhydrophobic coatings didn't last forever. Like maybe they're really efficient in that they work really well, but if it lasts forever, wouldn't it rather not be profitable?
No, a good question actually. Again, the reason paint companies make money is because you have to clean and repaint. Okay, that's a good point there. But many critical applications, if only you have a superhydrophobic effect, is very important for society. For example, water lines or oil pipelines. Imagine if you have pipes that are superhydrophobic that can utilize this effect to last for many years, even 100 years. Then we don't have much problems. Or critical elements in ships. And I'll give you one example of things that can be catastrophic. Not only of superhydrophobic, but materials in general. The big disaster that occurred in the United States, called the Macondo well, or the disaster that blew up essentially an oil rig, was a materials problem, a failure in the cementing or the rubber part. That damage alone was about $50 billion. Okay, so in many ways, superhydrophobic is good if it can last in many critical applications. But you're absolutely right. Maybe some companies do not want the superhydrophobic effect because they want to make money. Yeah. Good question.
The question?
Thank you for your nice presentation. And my question is just my curiosity. But in the example of products, you said there is a product that has antimicrobial properties. How does hydrophobic properties leads up to antimicrobial? Like, how does it repel, bacteria or other bio stuff?
Yeah. So the question really is what makes it antimicrobial or repel bacteria in the first place? So for a pathogen like bacteria to settle on a surface, it has to have different types of anchoring points. That could be molecular on the basis of, let's say, attraction of glycoproteins or essentially proteins on surfaces. If it wets a surface, most likely you'll have a pathogen. By preventing water from touching the surface in the first place, or preventing proteins from adhering to surfaces, then you provide a surface that is not attractive for bacterial colonization. Antimicrobial actually is a harsh term because that means that we employ a biocide, which you can do. So some of the superhydrophobic surfaces, you can put, for example, silver, or even different types of biocides. In our case, actually, we're working in combination with graphene. Graphene is actually an antimicrobial agent. But the first action of a superhydrophobic surface is to prevent proteins from adhering to a surface. The bigger problem with pathogens is not the individual bacteria, but the colony of bacteria that forms on a surface. That's called biofilm. So if you can prevent biofilm formation, that is a more important action.
Okay, any other question?
Okay, thank you for presentation. Since we're running out of time, I have several questions, but we can discuss later in the lab. But I would like to ask the question that relates to all of us. So, since you have given many examples of the collaboration industry in your lab, and I think, in my point of view, the coating industry is quite a developed industry because many of the needs are already accomplished by the several coatings. But so I want to ask you, but since you are still doing many collaborations, I want to ask you, how are you finding the other new needs for the kind of coating industry? So what is the mindset of thinking of the innovation of the coatings?
I'm glad you asked that. There are two mindsets. One is problem solving, and then the other is, of course, developing a new market. So right now, the problem solving approach means that there are some critical problems, especially in the corrosion industry, that can take advantage of this. And I usually talk to those companies who want to have a superior coating product for the marine environment, for oil and gas. So essentially asking problems or making them or helping them answer the problems. The other is opportunity. So the opportunity there is there room for a super hydrophobic coating, let's say in the paint industry or automotive industry, okay? It is for them an add-on, meaning they can make a super hydrophobic surface, but the question is there a customer willing to pay for that add-on value, okay? So most of the things that we buy are what we call commodities, meaning you pay them because they're cheap, but the question is, are you willing to pay more if you want to have this effect? So that's the market side.
Any other questions?
Thank you for interesting talk. I want to ask about, are there some techniques to control or switch the direction of the thermal conductance or water fluidity on the super hydrophobic surface?
A very good question. And in fact, because I ran out of time, I could not show you one example we have in the lab where we use voltage, electrical potential, to switch the super hydrophobic to a hydrophilic surface based on the redox reaction, reduction oxidation state of the conducting polymer. So that's one approach. The other is what I've shown based on a thermoresponsive approach. You can switch wetting to non-wetting simply by changing the temperature.
One more last question, maybe. Okay. Okay, so time is up. Let's thank Professor Advincula again. Thank you very much. Thank you very much for attending this lecture. Thank you very much for Keio University.